Well, welcome everyone to our webinar today. This is on interacting with data, and in that spirit we want to make the webinar as interactive as possible also. So as you have questions and comments as we go through, please jump in and ask those questions at any time, and Cliff will respond to them, and this will be as educational for everyone as quickly as we can. Very pleased to introduce to you Cliff Konold. Cliff is speaking to us today from the Scientific Reasoning Research Institute at the University of Massachusetts, where he is a research professor. He's been working for the past 25 years studying how people of all ages think about data and how they reason about chance events. He's applied what he's learned from his research in designing educational software. As a matter of fact, Cliff headed the program, the project team that developed TinkerPlots. Currently, he's directing a project to develop simulation software and classroom activities for middle school students, so he's right in tune with our topic and the things that we would like to talk about. Cliff, please tell us about TinkerPlots and how it can help middle school students to increase their quantitative thinking skills. But first, I have a question. Cliff, could you tell us about the origin of the name TinkerPlots?
When we were writing the proposal to NSF to fund the original project, very often when you write proposals, you come up with a product name or something that you don't really like. You don't know whether you get funded, and then the first 2 years of the project, you're trying to figure out what to really call it. And this time I resolved that I would come up with a name right at the beginning. So we spent a few days trying to think about the concept that we were building on, and it came out of that. So we envisioned a tool that students would really use to make their own graphs, sort of in piecemeal steps. And I grew up on Tinker Toys, where the Tinker came from. And that's the thing. The publisher, when they took it over, wanted to get rid of it. They were worried that kids would think it was childish. But I sort of insisted that, first of all, kids had no idea what TinkerPlots were, boys. And secondly, I've really seen that name tended to stick in people's heads. So I've seen an example where a guy couldn't remember the name of his own software, but he could remember ours.
Okay.
So, thanks for the introduction, Paul. Just in terms of framing what I want to do, I want to look at this quote from the Gaze report, where it reminds us that instructional activities at level B for the sort of the middle school age band of students should continue to emphasize the four main components in the investigative process. Have the spirit of genuine statistical practice. And I want to focus in particular on that word process and what we mean by that. In my view of this, what it means to talk about data analysis as a process is that it most often begins with a question we pose, and a genuine question about something in the real world, and often that takes the form of a question about a difference or a relationship. And then we go about trying to locate and sometimes maybe create our own data to try to answer that question. We then look at that data and interpret it to try and answer that. And almost always, if you're really doing data analysis on real questions, that's never the end, and you always come back to pose either additional questions or repose the question you started with. And so this is not a linear process that really has a fixed beginning and fixed end, but a very much a cyclical process. I'm often frustrated when I see what we typically do in the schools historically in trying to teach data analysis or statistics. And if you look at our current curriculum and the way we spend time, we spend almost all of our time in what I've got here is number 3. That is, we see our job as teaching students how to interpret some set of standard displays. And that takes up a good deal of our time. And one of the things I've been interested very much in is that if we view data analysis as inherently this give and take conversation between hundreds that we have and something in the real world, then the question is how do we involve students in that kind of conversation and get beyond just looking at graphs and how to interpret them. And are these screens updating as I press?
Yes, Cliff, they're fine with me.
So let me click this and go to symbols on it. Okay, sounds like we're ready to go.
Yeah.
This is a data set hosted in TinkerPlots of 24 cats. And the circles that you see over in this plot object here represent each cat. And so I can click on a circle, and it turns red. And over here is a data card that tells us all about this particular cat. So this is Bob Fuzz, a male who's 5 years old. I can click over here and go to case 4 that is Pepper. And you saw Pepper highlight over here as I did that. So each case here is a circle. If I click on an attribute, say gender, then all the circles get colored differently depending on whether it's male or female. And I'm just going to bring up a key here to remind myself that males are the yellow and females are purple in this display. When I click on a numeric attribute such as age, then rather than seeing distinct colors, I see a color gradient, where the lighter circles, like this one, belong to younger cats, and the darker the circle, the older the cat is. So here's a fairly old cat, Alexander, who's 18. So right now, the cats are randomly displayed in this plot object, and I can send them, in fact, into a new random order by clicking this mix-up button here, and they all go scurrying around to a different position. So graphing within TinkerPlots is viewed as the process of trying to organize these data that start out unorganized. And there are 3 general operators that students can use to organize data. One of them is this order command up here. So if I, with age selected, if I click on order, then all the older cats go over to the right of the screen. The younger cats are over here. If I instead click this vertical order button, they arrange themselves vertically by order of age. Another operator I can use to organize them is to stack them. So I can click this and stack them all up this way or that way. While I've got them in the stack, let me add their names to the icon so I can keep track. So I click on this label icon and add all their names. I'm going to go back now to where I can see the age color gradient. And with them all stacked and with their names, I can also order them by age simultaneously. So I'll press this order button, and now all the cats are ordered from top to bottom according to their age. So this is a very simple kind of organizational display that I might use to make judgments about the age of the various cats in this particular data set. I'm going to mix them all up. And look at their gender again. The third and the very important way to organize them is to separate them into groups. And one way to do that is just to grab on any cat. So I'll grab on this one and pull to the right. And I separate them now into males and females. I'm going to put them back together. Had I dragged up instead, I would have separated them this way. Let's switch to a numeric attribute, see what happens when we separate a numeric attribute. So with age selected, if I pull to the right, notice there are 2 groups, but now they're sort of divided by their mid-range. If I continue to pull, I can make more and more groups. So I've got 3 groups now. Let me stack them up. And as I continue to pull, I make more and more groups until finally they're right over their axis on the number line. I can make the icons bigger or smaller using this little slider here. Make them a bit bigger. And once I have a particular display that I think is powerful, I can just drag another attribute into the axis and replace the existing one. So let's look at body length instead of age. I'm going to click over here on body length. drag it into the axis and let go, and now the cats will rearrange themselves by body length. This is a kind of an intriguing display. You can take a look. We've got a lot of cats here around 17 inches long and another sort of mode at 21. And I should say that this is the data set I almost always use to introduce middle school students to TinkerPlots when I give this demonstration. And at this point, I always ask the kids, so how might you explain these two sort of clumps right here? And so I'll ask that question of you and make sure you're still there on the phone. Why do we get these two humps of body length? So anyone can speak up and we can all hear you.
I don't know.
You could investigate the other characteristics like gender or age.
So tell me what do you mean? How do you think age might account for this?
If you had a group of older cats, they might be longer cats.
Okay, so maybe I got older cats and younger cats, and that would explain sort of these two humps.
If we went from one variable to two variables.
All right. And how about gender?
And likewise, two categories. One of those genders might be bigger than the other, on average.
The males maybe are bigger, longer than female cats, so maybe these are males and these are females over here.
But then, of course, there could be two other categories. We might have domestic cats here and tigers in another group.
Okay. So yeah, we could have breed could explain this as well. So there are a lot of possible explanations for this. And by the way, up to this point, I was just showing how to manipulate TinkerPlots. And at this point, as soon as we have a question, we've just begun a data investigation. And students aren't happy just speculating about what might be. They really want to find out if there's anything to these arguments. And so let's actually investigate these two hypotheses. One was that age accounts for these two humps. So I'm going to click on age, the age attribute here. And when I do that, the icons are going to be colored with the age gradient. So they're going to turn red. And remember, the darker the cat, the older, or the darker the icon, the older the cat. So if age explains this, what are we going to see when I click on this age attribute?
Well, the ones under over 21 will be darker if it's the older cats.
Right, so I should see a darker red over here, a lighter red over here. So I'm not going to click on age. What do you think?
Doesn't explain it.
Doesn't seem to. And actually, most all students, this is down to fourth grade, will look at this and say it doesn't look like that explains it. Which is when that started first happening, it really surprised us a bit, because notice that what they're doing is making the judgments about two numeric attributes, which usually we put off till the high school when we look at scatter plots. And ordinarily, we'd look at the scatter plot of this data, which actually, let me look at that. If I pull up on one of these, I can separate them by age. And there's the scatter plot of body length by age. And that's a much harder display for even me to interpret and see no relationship than this one is. Well, let's go on and look at gender now. So I'm going to click on gender, and remember the hypothesis there was that these might be primarily males and these females. So let's see if that holds. And remember the yellow are males. What do you think?
I think the bigger ones are tigers.
So you don't think gender explains it very well either, huh?
I don't.
Of what?
Well,
It explains it better, though.
explains it better. So one thing that might help our perceptions is maybe ordering them by gender, sort of putting them together. And we can even separate by gender. And to my eye, anyway, that seems to explain a bit what's going on there.
It looks a little bit clearer, doesn't it?
Yeah, it's just reorganizing it like that helps a little. In fact, bringing them closer together sometimes helps me judge that. And if we knew something about means and how to interpret them, which when we start with students they don't, but if you did, you could click on see the location of the means in these two groups, or alternatively the medians. So that's a very quick just presentation of how TinkerPlots works and of how we use it to sort of get students engaged in real questions. And notice that one of the critical things that's doing anything interesting is having multiple attributes. Without those multiple attributes, we could have never tested those ideas that we had. And again, historically, I see some curriculum guides that suggest we start with one attribute and spend a whole year teaching students how to look at just one attribute at a time. And with one attribute or even two, you just can't do much in terms of getting a conversation going about explaining data.
And Cliff, this is marvelous how in just like 2 minutes you were able to do that, to bring out all of those important learning outcomes.
Well, thanks. Let me, I just want to get a sense now of some of the range of different displays and of how animating between them can help students. Young students have a lot of trouble interpreting even a display like this. Because this is a rather abstract display of a cat 20 inches long, as you have to already know the convention about reading a length off of an axis. And many students that we work with have a lot easier time with what we call value bars. And I'm going to switch to the value bar now. And in a value bar, the length of each cat is represented by a bar, who in this case, the length of that bar corresponds to their body length. It's almost like you're looking at these cats flattened out. And in fact, color them by body length and maybe even order them. Many of the graphs that you see in newspapers and that students will make if you ask them to make the graph data their own are really of this variety. That is, where a bar represents a case and its length. Most what we call bar graphs in the newspaper are in fact of this variety, and they're not frequency graphs. Often we'll start with students with this kind of a display, and then when it comes time to understand the frequency graph or dot plot that we were just looking at, we can animate to help them see that. So if I now switch back to my circle icon, watch how each bar shrinks to its endpoint. So now you can just view this as a bar shrunken up to its endpoint, and now I can stack them. And just do that smooth animation between one graph and another as a way to help students build that sort of understanding. So similarly, if I back up a little bit and make bins again, and go to a fused type of icon, I end up with a histogram. And histograms are really difficult for lots of students to interpret, primarily because they interpret each bar here as a case, just like the one we have. So they think this might represent a cat with a body length of, say, 8. I can, by the way, change my bin width to look at different shapes of this histogram. But again, to help students reorient and understand what this plot is, I can again switch back to a circle icon and watch these animate back into the circle icons that are much easier for students to understand.
So that was the best one yet, Cliff. That was the best animation shift yet. That was really good. That was so clear as to what was going on.
So let me just show one other animation. And a favorite plot of the student is the circle graph. And let's look at the pad color. This is the pad color of cats. So the colors sort of correspond loosely to black and brown and gray. And if I go now to a fused circle, you can see each of these cases now becomes a wedge in a pie graph. And if I now order them by pad color, I can sort of see in that circle the various frequencies of those different pad colors. So again, our attempt here is to show the relationship between each type of graph by doing smooth animations between them. Let me switch to a different data set to get back into some questions. This is, by the way, I'm not showing how to enter data. A new data set up there, I should just say that pre-built, but you can start from scratch and build your own data set.
I would be interested in seeing a little of that maybe at the end if possible.
Let me just show that to you briefly right now. Well, okay, we'll do that in a minute. So this is a data set of the 50 states, and it shows the capital of each state, the year it was the state was admitted, the longitude and latitude of the capital, and various information about the state, including information about educational spending, student scores on the NAEP, math and science scores, and then several attributes on teen pregnancies and drugs and weapons and things. Let me investigate this by first of all just clicking on longitude here and separating these out. And go here to latitude and separate up. And of course, I'm making a scatter plot. Let me bring it together a little bit. But this isn't a scatter plot we'd want to fit a line through, a regression line. You should be able to make out a rough outline of the U.S. Can all of you see that? So this is sort of the East Coast, the West Coast, Alaska.
That's really cool, Cliff. That really is.
So this is just because we're showing the longitude and latitude of capitals, we get a rough sense. We can already see the U.S. And now if I click on various attributes, I can pick up a lot of information just by seeing the displayed on this sort of map. So here's population, measured in millions, so the darker red, the higher population. Notice how that picture changes if we switch to population density. Here's the percentage of people that voted for Bush in the 2000 election. And this codes them according to the famous red and blue state. Let's just look at annual rainfall for a moment. So this shows the number of inches, average number of inches per year in that state. And that gives us probably a picture that doesn't surprise a lot of us. But I want to pull out another graph just to look a little more closely at what's going on. So I'm just pulling a plot down here, and I can have more than one graph at once open. And I'm going to separate rainfall here and stack it up. And notice this plot gives me a very different, raises a lot of different questions than this display of rainfall does. I see sort of these clusters in this graph, and the question that comes up very quickly is, well, do these clusters sort of correspond to sort of regions of the country? And to explore that, I'm going to turn off the color gradient by clicking on this little blue spot here, which is going to allow me to highlight different parts of this graph and see where they are up here. So let's click on these. Where do you expect these states are if they're together? Well, are you with me? I'm going to highlight all of those, and you can see that all of those really do belong to sort of a fixed desert region in the U.S., and that doesn't surprise us too much, maybe. And this is a very important statistical technique of being able to highlight cases in one graph and see where they fall on another one. How about these? When I highlight these and let this go, what's going to light up above? Where do you think these states are, the high rainfall states?
Mid-Atlantic.
Mid-Atlantic. So you're thinking about right around in here?
Right.
So sort of the Appalachian range?
Appalachian? Yeah.
Okay, let's test that out. We click them.
Oh!
Yeah, and that surprises everyone. Almost everyone has that intuition. And yet as soon as we see that, and then we think about the storms coming off the Gulf, it makes quick sense.
Plus you have Alaska over there.
And Alaska, yeah. Where is that? Is that the... It's not the furthest out. Okay, so let's continue our exploration. So we've got all these things in the middle, and there's almost even 2 clusters in here. So let's highlight this one and see if that's your Appalachian range. And that pretty much is. And then this is the leftover, but again, where do they? These sort of Mississippi Valley region, if there is such a construct. So again, this ability to be able to click on cases and see the link in all of the displays between them. So I click it here, I see it highlighted here, and I see that case at the top of my data card, is a really important data analysis technique. There are a lot of other tools that we, well, let me undo that we involve students in using before they do summaries using means or medians, and one of them is sort of using reference lines that help them sort of read off values or even just mark cases. And another really important one are these dividers that allow students to sort of mark and talk about a range of cases, say in the middle, by being able to really highlight them, and then to be able to come up here and turn on this N counter and be able to count the cases in these regions. So this is actually where, when we're working with students, this is the kind of analysis we have them begin doing the distributions before they use means or medians. It makes a lot more sense to them to talk about cases in the middle than it does initially to talk about where the average is, so by clicking on this. And we turn those off. We've invented sort of a display called a half plot that sort of shows where the center part of the data are. And of course, if we're using percentiles to measure that half, that's basically the box plot, only simplified. So I can move to the box plot here and see a box plot of this rainfall. Again, having the data under here at the same time, students see this box plot really helps them to not lose track of what they're looking at. Let's click that off. So does somebody have a question they want to look at? We've looked at rainfall. Can someone suggest a question they'd want looking at some of these other attributes?
Teacher salaries.
Let's pull teacher salaries. And then this is data from about 2000, remember. Let's stick it right down here.
It probably hasn't changed a whole lot since then.
Unfortunately. So there are teacher salaries. Now what do you want to know? Let me make these cases a little bigger. Well, I know what you want to know. You want to know who's up here. What do you get? Who's at the top up here?
Connecticut.
Let's click on it. In fact, it is Connecticut. You can see it here and here. It might help if let's bring up that table of our data up here. This is the more standard sort of display of row column table of the data. So when I click on a case now, we can find it more quickly, maybe over here. So, and who's right below Connecticut? New Jersey? All right. We got a New Jersey person here?
Yeah, afraid so.
Well, you're forgiven, I guess. Of course, we want to know who's on the low end down here. South Dakota. Let me turn this off so we can see it up there. South and North Dakota, Mississippi. So suggest another question about teacher salaries that you want to explore.
I'm wondering if there's a connection between teacher salary and NAEP score.
Uh-huh.
If you pay the teachers more, will the kids do better?
Okay, so since we're math, let's look at math NAEP. And let's just start by clicking on the gradient and see if we can see any relationship there. So remember, if teacher salary is related to math NAEP, we ought to see the graph get darker and darker up there. When we click on that, first of all, what are these gray areas? Well, these are states that didn't report NAEP scores that year. They weren't. Not all states have to do the NAEP, or at least they didn't then. But that certainly doesn't look like much there. So let's pull it up into a scatter plot. And now our missing cases, by the way, are all over here out of the way. And there's the scatter plot of teacher salary and NAEP. Well, there's something wrong with the teacher salary as a measure here, in some sense, because, some states it costs more to live in, right? Yes. So let's just take a look. Let's go back to teacher salary and back up. And we don't have cost of living measure here, but we do have income per capita, which is maybe something like that. So let's see what the relationship is between income per capita and teacher salary. So I'm going to click on income per capita and do a scatter plot. And this shouldn't surprise us. So the higher the income per capita, the higher teacher salary. So if we wanted to know what states compared to income per capita pay their teachers relatively well, which states are those? Or at least, what are we looking for in this circle for a state that pays its teacher relatively more than other states?
So circles that belong above the line. If we do a straight 45-degree line.
Right, so I don't have a line to fit. I've got a drawing tool though. So basically, if we drew a straight line through here, more or less, states that are above this are paying their, well, let's think carefully here. States that are above this are, let's switch the axes. I want to think, I'm going to clear this drawing. I'm going to swap the axes. And I don't know if you find it easier. I often find that there's one direction I tend to think about this. So now income per capita is here, teacher salary. So the teacher that is up here is sort of higher than you might think they would be based on their income per capita. So what state is that? Michigan, Pennsylvania. Here's one that's really low. So given their income per capita, they're a lot lower than you'd even think they were. South Dakota, North Dakota. So if we wanted to explore this question between teacher salary and NAEP scores, we might want to construct a new attribute that sort of scales teacher salary by income per capita. Right? We can in fact do that real quickly. We can make a new attribute here called, we'll call it scaled salary. Oops. Can you just No. I'm going to click here, and this is going to be a new attribute that I'm going to define by dividing teacher salary. Oh. Sorry, I'm hitting keys that I'm going to divide teacher salary by income per capita. And so now I've got this new scaled salary. So if somebody is making about the same as the income per capita, they might have a score of 1. And so notice all teachers are actually making at least above the income per capita value. They're above 1, and these are the states that are really doing well, which are Michigan, Pennsylvania, and these are the states that are doing very poorly, South Dakota, North Dakota. And now let's put NAEP math scores in there and see what we see. Although that looks interesting. Might want to spend some time looking at that.
That was where he was. That's the whole lot.
Well, what I'm trying to do here in the last few minutes is, again, give a sense of what happens as soon as we start looking at real data when we have multiple attributes, is that we can start asking questions that we care about, and exploring them usually leads us deeper into the data. That is, we seldom get a direct answer right off. We often critique the data that we have, look for better data, think about how to redisplay it, and move on. So what I've really been, I want to pull back from this particular question now and just, again, focus on what we mean by data analysis is a conversation that really flows, should flow ideally, very quickly between questions, displaying data, interpreting it, asking new questions, reformulating it. And just too frequently, again, in the classroom, when we try to pull this off, and especially by having kids design surveys and collect data, it moves at such a slow pace that the excitement about the question can often get sort of drowned out and lost in the slow pace of data collection and kids making a single graph that can take them by hand a whole day. And here what we're able to do is, because we've got multiple attributes already collected, and because we can make graphs on the computer, we can move very quickly and keep interest going. I think that's one of the sort of the biggest advantages of doing data analysis, even for students on the computer. It's this ability to really get into a question and keep focused on the question we're interested in, rather than the details of carefully making a graph, labeling the axes, collecting new data that could take weeks. Let me just, because somebody asked, are you caught up with me now?
I think we are. One more question on that test. So after you manipulated the data and found the relationships that are of interest to you relative to the questions, can you then save that for reference in the future when you want to come back to it?
Sure, I can save this right now as a document and do a save. And when I reopen this, it'll open just like this.
Yeah, right.
That's and in fact, if our students are working on it, they can pull out text boxes and type in descriptions of the plot, and so they can really make this into a reporting environment as well. So I can have several text boxes with any number of graphs that I want. While I'm here, let me also just mention the fact that this data is not data that would be appropriate for middle school students. This data on states. Really put this together specifically for using with teachers. But it's important to sort of look at this data and think about why it wouldn't be useful to students. And there are at least 3 reasons that this wouldn't be good. One is that almost all of the attributes are percentages and rates. So population density, median age is already an average. And students really are struggling to understand what rates and percentages and averages are. And so to have a data set in which all the primary values are already rates really presents a hurdle to them right off. Secondly, a lot of the attributes are things themselves that they may not either understand very well or even care about. So income per capita is not something that would mean as much. Forget even about the per capita. Income itself would not be something they could wrap their heads around and decide whether it was a lot of money or not a lot of money.
Mm-hmm.
Same with teacher salaries. They make $28,000. And related to that, the kinds of attributes that we've put up here included on teacher salary and NAEP are really attributes that we know teachers are going to want to explore and care about. They are not attributes that students are going to have much interest in. So when you're thinking about a data set for students, you want to think about the particular attributes that make it up, the kinds of background knowledge that students can bring to it, that's the kind of knowledge that allows them to pose interesting questions and care about getting answers to those questions. And finally, what are the measures? Are the measures something that they can understand, or are the measures that they will have very bad intuitions, poor intuitions about? So just, if we were starting over and wanted to build our own data set, if I go up here and say new, can you all see a blank screen now?
Yes.
I can just pull out a blank set of data cards and click an attribute here and begin to build a new data set. So I might put a name, say years teaching. Oops. I'm sorry, I hit my master keys here and say I've spent 30 years. So that's case 1, and I can go on to case 2 and put in information for Rick, and on we go. So you can just start from scratch like that, and as soon as you've got 2 cases, you can begin to make a plot of that information.
And you can save that also, right?
And I can save that right now. Now, another common source for data is the Internet. And I just want to show quickly one example of how you can use TinkerPlots to quickly pull data off of the Internet. And this could involve some lag time, so I'm going to need, I'm just going to delete these here and have a blank data set. And I'm going to pull up my web browser. And I'm going to wait until all of you hopefully can see that web browser up. I've got my Google page up. How many, can you sound off if you can see my Google page?
Yes.
Yes.
So I'm going to just type in the name of a source that I know has a lot of data on it called Dazzle. And that brings up, the top hit is the data and story library. I'm going to click that link. And this is a really nice source for data. I would think most of the data sets are probably a bit better for high school and college than they are for middle school. But let's click here and go to data subjects. Can you see a list of subjects now over on the left?
Mm-hmm.
Okay, let's go to food. And there's a whole bunch of data sets on food. Let's look at the serial data file. And this shows you the data. So this is a data set of a bunch of cereal names and tells you information about the name, the calories, the amount of fat, carbohydrates, sugars. So that might be interesting data. To get that into TinkerPlots, the sexy way to get into TinkerPlots is to go up here to the URL and just click on this title, and I get a hand. And can you see that? I'm just going to drag that URL from the web browser right onto this empty TinkerPlots document and let it go. And TinkerPlots has a routine that helps it find the data on that web page, just the data, and bring it into TinkerPlots. Can you all see that? The TinkerPlots file now?
Uh-huh.
And so now I can pull out a graph and begin instantly looking at, let's look at the calories in these various types of cereals and stack them up. and I don't know what type is, manufacturer. So on we go. So that's, you can also get data from just simply from an Excel spreadsheet by just copying all of the information and going to TinkerPlots and pasting them into a set of data cards. So it's very easy to move data from those kinds of applications into TinkerPlots.
Amazingly easy.
They're structured in the way TinkerPlots expects, which means that we've got a bunch of rows that are cases and columns that are attributes.
Right.
So other questions?
Are there activities that have been developed that go directly with these built-in data sets, Cliff?
Yeah, there's a small set of activities that comes with the software called Exploring Data with TinkerPlots. And then there's a new book that just came out that's published also by Curriculum Press that is called Digging into Data with TinkerPlots. That's, I would say it's about 3 months of activities if you want to spend that much time for middle school students, all written around TinkerPlots, and some additional new data sets that don't even come with TinkerPlots.
And those are at the middle school level?
Yeah, that is specifically for the middle school.
Yeah.
The other thing, I think, how many data sets are there with TinkerPlots? I think there are 40 or so. So with each data set, there's a no, it's not going directly to the data set. I won't show that. So with each data set, we've included 1 or 2 questions right below the data.
Right.
That if you wanted to, you could just sort of have students open it up, and the question itself can get them going. Let me just say that with data sets of this sort, where there are multiple attributes, it's in general not a good idea just to give students the data set and say, see what you can find. Having a question is really, really important. And it's really easy to branch off a single question and get going. But without that single question, most people will sort of flounder for an unnecessary amount of time.
Right.
And there are some questions that are just pretty rich and others that aren't. And so you really want to focus students' attention on questions that really, really are going to provide a sort of a rich investigation. So if I was just pulling up this serial thing, there's just so many attributes, I wouldn't know where to start. As a teacher, I'd spend a few hours looking at this myself and decide, well, what are the questions that sort of produce interesting graphs and interesting questions, and focus students on those. Some other questions?
Show us one more time, Cliff, if you would, how you changed the axes on the graphs. You did that so magically. It was marvelous.
So if I've got calories here right now, and let me get rid of the other one, and I want to see, instead, I want to see a plot of the sugar levels, I just grab the attribute name on this data card, the hand closes, and I come down here, and that axis highlights, and I replace it. So I'm just replacing calories with the attribute sugars. So now we'll go to vitamins. That's interesting. 25. By the way, this is really important. If I go grab this data set, notice how I'm stranded now, and I'm saying, well, what is vitamins? And that information is back where I got the data, where they had all the information about what variable names are. I'm going to copy those now, come back into TinkerPlots and pull out a text box and paste that text here. So I've got that. And now I can come up here and say, well, That doesn't help me a lot. Grams of sugar. No, vitamins. Vitamins and minerals. So they all measured at 0, 25, and 100. And that's the typical percentage of FDA recommended. So this kind of metadata is so critical to analyzing data, and very frequently people neglect to bring that along. And I would add to this, the other thing you want to bring is the source. Where did you get it? So I'd come back here and I'd copy the URL and paste that here. And now I can really get back there if I need to and get it. Again, I've encountered so many data sets that people send me, and they don't know where they got it from. And it's almost useless, right, that form.
So to confirm then, interfacing with Excel is just perfect, right? It matches 100%.
Well, it's in the sense that you can copy cases in Excel and come into TinkerPlots and just use a simple paste command.
Right, right.
So it's reading that text-delimited file in that form off of that. Other questions? Well, you can, this is, TinkerPlots is a key click and impress product, and you can go onto their site, and if you don't have a copy of TinkerPlots, you can download a demo version that you can use for about, I can't remember, 60 days maybe after you first start it. That has all of the capabilities you've seen, except I don't think you can save data or print them. So, but it's other than that, a fully functional application. So that gives you some time to play with it.
Cliff, thank you very much for sharing all of this today. TinkerPlots is obviously a very useful pedagogical tool.
Well, thanks, and thanks for having me again.
We appreciate it. Thank you so much.
Bye-bye.